All right, recording is rolling. It is Tuesday, November 7th. Oh, here's top scientists for energy. So awesome job if you're on that list. Actually, I might make one all video today. So just in case I end up using this one, here's for honors. Of course, you guys got different type quizzes going on. So yeah. All right. So yesterday we started momentum. You guys remember? I'll flash this poster up here. Probably helps. Right? Momentum is mass times velocity. This is a vector value. So we're back to directions mattering. Right, it's going right or left. This is value that's conserved in closed systems. Right. So just like energy, the last couple weeks, you can't create or destroy momentum units. Right. A unit of momentum is I'm just going to call it kilogram meter per second. Sometimes you see the unit Newton seconds, but it doesn't have its own special name besides that. Okay? There you go, kilogram meter per second. And it's involved in collision physics. Whenever you see a collision, the first thing you should think is this framework right here. Okay, something to do with like mass times velocity. Mass times velocity is conserved during the collision, right? With the exception of if you see something like falling on a spring. If there's a collision with a spring, then don't think about it. But if there's like two masses colliding, then think something like this. Okay. So I got to start a question here. This is a good classic physics question. Start a question that involves collisions. Right? Let's do comparative collisions. How's that? Zoom. All right, record resume. So let's say you got a couple of bullets. Maybe I've got like a steel bullet and a rubber bullet, and they got the same mass and they're fired at the same speed, right, towards these, let's say, wood planks, right? They're standard, right? Okay. And the steel bullet is going to embed inside that wood plank, and the rubber bullet is going to bounce off the wood plank, right? Now, so which of these above scenarios is more momentum transferred to the block of wood, right? Or, okay, and therefore more likely to knock it over. All right, yeah, thanks. Okay. Yeah. Here, got that. Okay. All right, so yeah, I'll tell you that they're not equal, right? One of these scenarios, there's more momentum transfer to the wood, and maybe it's like they're on the verge of toppling over. Right? Suppose only one of those actually topples the wood over. Right? Which scenario would it be? Okay, well, it's going to be the one where it transfers more momentum. So which one is it? Is the one that embeds in the wood, or is the one that boing bounces off the wood? Okay. So what do you guys think about that? So you guys rest up with today. Okay, so we did top scientists. I think next couple of days I'll have you guys with the collision carts. Right? So I'll have you guys set up a table today and then get some measurements tomorrow. And then yesterday we started on this half page. We solved, I think, just a couple of problems. So we're going to do more of those today and see where we get by the class there. All right, so let me see, show of hands what you guys think on this. Okay. Either, so which one transfers more momentum, which one's more likely to topple over? Is the one that embeds or is the one that boing bounces off? Okay. Show of hands, how many guys think that the one that embeds is more likely to knock over? How do you think the one that boing bounces off more likely? Oh, yeah. Oh, you guys got it. All right, seeing a bunch of hands on this one. You guys are right. This one transfers more momentum. Okay, so why would that be? I'm going to throw some example numbers on here. Let's say I got how about 1 kilogram bullet moving at 100 meters per second? Now, that's ridiculous numbers. They got like a big like slug bullet. All right, let's do 1 kilogram moving at 100 meters per second. So if you got 1 kilogram moving at 100 meters per second, that's like a momentum of 100 kilogram meter per second, right? And if that embeds in the wood, then now the transfer momentum, I'll just call it P, right? Or how about this? How about delta P, right? So delta P for the wood. Well, it wasn't 0. It's about to gain the bullet, which is, this is an inelastic collision. So from the point of view of the wood, the acquired momentum, the change in momentum is 1 times 100, that's 100. I got kilogram meter per second, right? Right, remember, all these numbers should have units attached to them, right? Unless it's like a coefficient or something, right? But right, more often than not, this class, right? You guys got units attached to numbers. Right? But what about the rubber bullet? Right, so you plank of wood here. Right, and let's say fire it, same thing. So got 1 kilogram, kind of big number, but let's just go with it, right? Let's go on that speed of 100 meters per second, right? And then it boing, right, rebounds off. Let's say it rebounds the other way at, maybe I'll just pick something up, right? How about 80 meters per second, right? Like 80 meters per second, right? pretty elastic. Maybe you got a relatively heavy block of wood compared to the bullets on there. Okay, so this one, how much momentum was actually transferred into the wood? Right. Well, guys, what's the difference between 100 meters per second to the right and 80 meters per second to the left? What's the difference? 180, right? Multiply, so it's meters per second, multiplied by the mass. So how much momentum was transferred into the wood? 180 kilogram meter per second. Yeah, right? Which is almost twice as much. That's kind of like the limit to what could be transferred, like theoretically, like if you have like a 1,000 kilogram block of wood or something crazy, right? And you have a collision that's really close to perfectly elastic, then this rebound speed could be maybe up to 100 meters per second. Couldn't quite reach it, right? Okay, so yeah, so this transfer momentum could be up to twice as much because it rebounds. Yeah. Somebody caught the question there. Let me show you guys the honors version of this. So this is off the honors page. One of the first questions they get is number 55, bullets. 2 bullets equal mass are shot at equal speeds of blocks of wood on a smooth ice rink. Ooh, okay, so they got rid of friction. Right? 1 bullet made of rubber, but boing bounces off the wood. The other made of aluminum burrows into the wood, which case does the block of wood move faster? Explain. Okay, so that's just a variation on what we said. Okay. All right. Next thing, let's look at lab for tomorrow. All right, so break out. Got this track. I think we used this track back in the day for your car and incline lab. You're going to send to an incline, right? Dropped up so it's 100 degrees. Oops, zoom out where it's visible. Okay. All right. But what this actually comes with, it's actually a kit that comes with these carts, right? This is like a low friction type system, right? So once you get this going, it's just very little stuff. There's not friction. It'll eventually slow down, okay, but not a whole lot. Okay. So these carts too, they have magnets in them that are all the same pole, right? So they'll bounce off each other really nice. So you guys can see it, you bounce them off each other. Okay. Something else you can do is you can stack lab weights in them. Okay. Now I know one empty car by itself is 500 grams. You have to call that half a kilogram, right? So it's like another half kilogram. Right? Ooh, what happens when I apply it like this? Or got my lights in the way here. Yeah, confined space going on. Okay. Right. So tomorrow you guys get to play with these cards. Now we're going to do a simplified version tomorrow, and I think the next day I'll have you guys do more general collisions. This could be a general collision that is pretty close to elastic, maybe not perfectly elastic, but close to that end of the spectrum. But I'm going to have you guys do this. Turn this car around. Oh, look, I got some magnets taped on. Some of these bar magnets. These bar magnets look like these right here. Okay. And if I tape it so that I have opposite poles, some of these are going to stick together. Oh, just like that. Ooh, what kind of collision is that called? Inelastic. Yeah, inelastic. Right. And I think this one's easier to work with because after the collision, there's only one speed, right? So that's like less data to have to juggle around, right? Okay. So yeah, you guys get masses, you guys get speeds. Maybe I should say velocities, right? Because maybe very simply, one could start at rest. It could start with 0 momentum itself. Maybe that could simplify it a little bit. Okay. And you guys gonna say how much momentum is transferred, or well, I should say, is momentum conserved, okay, which ideally it should be, or pretty close. And also maybe check for kinetic energy. What did I tell you guys yesterday about kinetic energy for an inelastic collision? What happens to the kinetic energy before and after? It should always do what? Yeah, decrease. It should decrease. Right? And if you're ever asked to explain why in an FRQ, then you would say something like, oh, well, maybe there's like permanent deformation. Normally, if you have like blobs of clay, there's some force synthesis that goes into that, something like that, right? So this is a really stripped down lab table. You guys probably want something a little bit more elaborate than this. Here, if you guys got some paper out, let's go ahead and make this lab table. If you don't have any paper, here's a stack of paper. Bam, right there. You need some paper. Right. I'll make a lab table. Where you guys make a lab table, I'm gonna put more columns in this. How many columns we got? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay, but I want to do a lot more columns than this. Right? So at least these last two, it'd be nice to track how much momentum total before the collision, how much momentum after the collision. I might want to keep track of that. Okay. But then, like, how are you going to get these speeds? And there might be more than one way to do it. So one way you could get the speed is you could use the speed gate, and you could have masses that, or I've seen students take. I remember last year students had a creative idea to use glue sticks. They just put a glue stick on top of the cart, and then as it went through the gate, it could measure its speed. Right? That's one way you could get the speed. You could do a direct measurement. Another way you could get the speed is you could look at the meter stick function on the side, and you could also have a stop. Oh, do I have a stopwatch up here? No. Okay. Well, you could use. You guys know stopwatch, right? So you can measure the time. How far does it move, and how much time? Right. But that would be extra columns. You could do it that way, right? You could slip in some extra columns, so you could calculate the speed. Right. Is another way to do it. Right, so just put your name on your paper. Right. Let's call this inelastic collisions lab. Right. Okay, so I need at least 8 columns, but maybe more than that. Right? Maybe I'll make another couple columns to keep track of kinetic energy, so that's 9, 10 columns. If I do some kind of lead in to figuring out what are these speeds, well, I would need distance and time for each one of these. So that's like each of these 3 times 3, right? Distance times speed, distance times speed, distance times speed. Okay, so it's let's see, 9, 10, 11, 12, 13, 14, 16, right? I could have up to like 16 columns on this table, right? But depending on how you do this, right? I'm gonna give you guys some leeway, so like some creativity tomorrow to figure out like exactly how do I want to figure out what the speed is? Do I want to directly measure it? Do I want to calculate it? Okay. See if I do 16 columns, ooh, okay, each of these should be like 1.5 centimeters. 6, 9, 12, 15, 16. 21. Okay, so you guys are making this as I'm making this, right? And so when you guys come into class tomorrow, you'll have this table all ready to go. Okay. Now this is just the inelastic version of the lab, which should be like the easier one. Okay. Also today is tomorrow is a slightly shortened day because we're gonna have one of these mental health days. Okay. Okay. And then Thursday will be a little bit longer day. So when I have you guys do the general collisions, it'll be even a little bit more complicated than this. This is like the simple version. Okay, so I got at least 16 columns going on. Okay, something like that. Okay, so I got to have different trials, and like 1, 2, 3, 4, 5. Right now, you guys know on the AP exam, if there's some kind of independent variable, they want you to do multiple trials for that particular variable, right? And then like do like 3 times to take an average to reduce error, right? Oh yeah.
How many columns are there?
I have at least 16. Yeah. Okay. Which you may or may not need. Okay. So I'm not gonna have you guys do like change some independent variable necessarily. I mean, yeah, you want to change something. Maybe you want to change masses of cards or something, right? But tomorrow's kind of gonna be an exploratory type lab. So just have different collisions, just get some measurements, just test it out, see like is momentum conserved or not. So you want to keep track of what's mass of cart A, mass of cart B. Right? Oh, I forgot to have a row for units, right? I definitely need a row for units, right? Right. You guys have units attached to all these numbers. So like kilograms is probably a good choice. I guess you could do grams. You'll just get really big numbers, but kilograms is probably a good choice. Right. So the speed before the collision for each of the car. Well, actually, I guess one of these could be 0. Maybe we should do that. That could bump off a few columns. Maybe I don't need exactly this many columns, right? Let's have, maybe I'll set it up that way. I'll say, so what's the distance that cart A goes in some time? So that could be like, oh, maybe like centimeters and seconds, or you could do meters and seconds, right? That we do, right? Therefore, what's the speed of cart A pre-collision? That could be in like centimeters per second or meters per second, up to you, right? Yeah, cart B, I'll just define as 0 centimeters per second. I'll just call it 0 all the way on. 0, 0, 0, 0. Okay, right. Just to say that cart B is just starting at rest. Okay. And then the speed after the collision, or so the velocity after the collision, post collision, right? I'm saying A plus B because inelastic, they're going to stick together. Right? Now, how could you get that? Right? Well, you could directly measure it with a speed gate, or you could go, how far did it go, A plus B, and how much time? Therefore, what was the post collision velocity? So this could be maybe in centimeters, this could be in seconds, this could be in centimeters per second, something like that. Right. All right. And then what was the momentum in the system pre-collision? You could say the sum of momentum, but since they got one cart starting at rest, that would also be momentum A, right? And then what was the momentum post-collision? So maybe I'll go momentum A and B post-collision, right? So it'd be like the sum of the masses times the post-collision speed, something like that. Okay. Something else I want you guys to keep track of is what was the kinetic energy before the collision? Right, so I'll put a subscript A because there's only one cart in motion, right? Versus what was kinetic energy of the two carts together post-collision, right? Like pre and post, right? I think that's pretty good right there, right? How many columns do I actually have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, ended up using 14 columns there, right? But yeah, like tomorrow's gonna be an exploratory type lab. If you want to set up a little bit differently or try something a little bit differently, right? As long as you have them colliding and sticking together. Yeah, but I think this is pretty good. Good recommendation there, right? Right. Okay. So yeah, my pre. Oh yeah, go ahead.
Does that say XA plus B substrate?
Yeah, X A plus. All right. Okay. Here's what. Okay, because if you guys know what's going on, then you'll know what the subscripts are. Okay. Okay. So we keep track of what is mass A, what is mass B. Right. So that's my two individual carts. This could be A and B. You know, a blank cart is 500 grams. Right. You can call it 0.5 kilograms if you like. Okay. I need to figure out how fast was one of the carts going pre. And you could either directly measure it, like put a glue stick on the cart and have it go through this gate, right? Directly measure the speed. Or you could do what I did here, open up a couple of other columns, say, well, how far did it go in centimeters and how much time seconds, right? Now that's a little bit more equipment, maybe so it's a different way. You could calculate this, right? Now I have my second cart just starting from rest. So I just did a single column for the speed of cart B and just call it 0, just have it start at rest, right? I think it's maybe a pretty good thing to do, right? If you want to be a little bit more adventurous and give it a push, then figure that out. That'd be extra stuff to, right? And then what about post collision? So I need the speed post collision. So this is V post, right? And that's for A and B stuck together, right? You could again either directly measure it, or you can say how far did it go and how much time. So that's X sub A plus B and how much time A plus B. Right? A plus B is the two carts put together, right? Which is all post collision. Therefore, you can calculate the momentum pre-collision and post-collision, right? Because it's just mass times velocity for cart A before the collision, and then mass times velocity for the sum of the carts post-collision. Right? You can also check kinetic energy, and kinetic energy should decrease. That's sure 1/2 mv squared for cart pre-collision versus 1/2 mv squared for both carts stuck together after the collision. Right? You guys see that? Okay, I forgot that. All right. Okay, and then this pre-pendant table is like a really boiled down, simplified version of that, right? But really, maybe you want something like that. Okay. Okay. All right. I think everybody's got this. Everybody's got this. All right. Another thing I want to mention, because I've done this lab, number of years. I see students come across like the same sets of questions and make the same mistakes year after year. So I can tell you ahead of time like some of the things that you're going to run into because I've seen them. Right. Right. One thing is if you do this method that I did, like you want to calculate the speed by doing how far and how much time. Something that I've seen students do over and over and over in the years, I guess maybe it's just intuitive to do, is to measure the distance that the cart comes to a stop. Now, if the cart is rolling to a stop, it is slowing down, isn't it? Right? I mean, the idea is like of a low friction surface is that there would be no friction and the cart would never stop. So the velocity would be constant. So you can say, oh, well, it goes whatever distance and how much time, and then it's going that speed, right? Now, if it is slow to a stop, then you know that speed is not exactly constant. So ideally, you want to maybe get like the first like 20 centimeters and however much short time interval time, right? Which is kind of hard to get, right? Because if these carts are moving at a good speed, and you want to say like, what is the immediate post-collision speed? But before it really starts to slow down, right? Then maybe you want to get like in some short interval of time, how short distance does it move, and then you can get a pretty good idea, right? But if you let it roll all the way to a stop, then when we put on a graph, what's going to happen, right? And I've seen this happen over and over, right? Right. Maybe you could do that, and that actually could be a good idea if you know what you're doing. Right? Here's why. Right, let's do velocity versus time, v versus t, post collision. Right. So I'll put time on this axis, say in so many seconds. At this moment, at time 0, that is the collision. Bam. Right. So this is the collision right here. Right. Or the time of the collision. Right. And what is the speed of carts A and B put together? It could be in centimeters per second, for example, meters per second, if you like. Okay. Right. Well, I should ask you guys. What should that graph look like? Suppose it slows down uniformly. Right. So the collision happens, bam, at time 0, and then the carts are collectively moving together, and they're going to slow to a stop uniformly. Right. Let me walk around the room and see in your notes, since you guys are taking notes on this, what you guys think that graph should look like. What does that look like? 2 carts stuck together, flowing to the stop. Oh, Gavin knows what it looks like. Who else? Nathan knows what it looks like. Yeah, Zach knows what it looks like. All right. Okay. So, some of you guys, I may have missed a couple of guys, right? But see, there's some velocity here, right? Which is really the velocity you want. You really want to know, like right after the collision, right, how fast they move it together, right? That's what you really want to know, right? But since there actually is some friction, then it's going to do this, right? It's going to slow down until it goes to 0 velocity, and then it comes to a stop after some time interval. Isn't that exactly what it would do, right? And this is assuming uniform motion, so like it slows down at a constant rate, right? Oh yeah, speaking of which, what does the slope of that line represent? What physical property? Acceleration, right? Now, if there really was no friction, if there was no friction, then what would this graph look like? Should just be a flat line, right? That's if no friction, right? So what you really want is you want to get what is the post-collision velocity. You're really trying to get this point, right? Right? Because if you do total distance to a stop divided by the time to come to a stop, right? If I call this v post, like post-collision, which is really what you want this number right here, right? If you do total stopping distance over total stopping time, what does that actually tell you compared to the speed of the, like let me tag some numbers to make it make sense, right? Let's say the post collision speed is actually like 10 meters per second, just make something up, 10 meters per second, right? And you let it roll to a stop and you say, let's see, it went 10 meters and it rolled to a stop in 2 seconds. If you divide that out, how many meters per second does that say? 5 meters per second, which wouldn't that be half of the original value, right? So if you do total stopping distance over total stopping time, you're actually getting the average velocity while it's stopping, which is going to be half of the true post-collision speed, right? Again, like over the years, I've seen this over and over and over. Students like naturally do that. And they say like, why does it have exactly half the momentum that it should have? Like however much momentum it started with, they was, wow, momentum should have been conserved, but it's always half. Why does it always half? It's because you, and I always ask them, well, did you time it when it rolled to a stop? And say, yeah, that's what we did. So that's why, right? Because you're getting half the post-collision velocity, right? This V bar is actually V post, which you actually want, divided by 2, right? So if you use that method, then you're going in ahead of time knowing that, So if you let it roll to a stop and you do stopping distance over time, then what I would do in that case is I would have an extra column here. I would say, well, I did average velocity, and then the true post-collision speed would just be that times 2, right? Maybe you could slip another column in right here, right? You guys get that? Right, that's if you want to do that procedure, right? You guys get that? Which could be a good way to do it, right? All right, you guys got on tomorrow's lab? You guys got the table ready to go? Right, you'll bring that in tomorrow, and then yeah, I'll give you guys some collision cards again for just the exploratory type lab. Just want you to do lots of collisions, get lots of measurements, do some calculations, compare numbers, say, oh yeah, the momentum should be pretty well conserved, and the kinetic energy should decrease. Right, so you can see for yourself. Okay. Right, let's do this half page. See what we got a little bit different places. Oh, looks like we did we got through number 4 yesterday, looks like. Okay. So number 5, you guys ready for number 5? All right, so here's what I've done so far. Number 3, number 4, just general conservation of momentum. I had to give you 5 of the 6 values, and then you can solve for the 6th one. Okay. Now, number 5, if you just glance at the table, already it looks a little bit shorter, right? Ooh, it looks like I only gave you 4 values, and I'm not asking you to solve for one thing. So what's this stuff? Okay. 2 objects collide and stick together. Hey, that's going to be tomorrow's lab. That's what I just spent last few minutes setting on the table, right? Okay. And a perfectly inelastic collision. That's what stick together is. Okay. Given the masses and velocities of the object, initial velocities of objects, what's the final velocity? Oh, after they stick together. So I got these 2 masses, right? And they're moving at these velocities. Oh, it looks like I have 2 positive velocities. I don't know if I did that on all the papers, but if I have 2 different velocity, positive velocities, this looks like a fender bender situation where a fast car is running into a slow car, right? And rear ends it, kind of thing, right? And they're going to stick together, right? And then how fast do they move together post collision? Okay. So number 5, right? I got mass A moving at velocity A initial, and I got some mass B moving at some velocity B initial, right? The fact that both velocities are positive, that tells me they're moving in the same direction, right? So maybe the fast one slams into a slow one, okay? Right. So I know there's going to be a collision, bam. So I'm going to do conservation of momentum, sum of momentum before the collision equals sum of momentum after the collision, like that. Right. And what was the momentum before? Well, it's mass A, velocity A initial, plus mass B, velocity B initial, right? And then after the collision, oh, well, they combine, make one giant mass. So that's the sum of the masses times velocity final together, right? And that's what we're solving for. So what is that? Post-collision velocity, right? You guys see that? Right. If AP asks collision, AP is going to ask lots of collision questions, right? They tend to ask questions like this, like perfectly inelastic, because the math is a lot more straightforward. Elastic, you guys saw was that crazy system of equations yesterday, but inelastic is just very simple, just that. Okay. So it's just pop in values. I got 1 and 5 kilograms, so 1 kilogram, 5 kilograms. Got 1 kilogram plus 5 kilograms. I've got, let's see, 5 meters per second, 5 meters per second, 1 meter per second. And then what is the post-collision velocity? Right. So does that look like, so equals, right. Does that look like 10 units of momentum? That 10 kilogram meter per second causes a total of 6 kilograms to move how fast, right? So whatever 10 over 6 is that. That's right, right. So the post-collision velocity is, I got 1.67, and that's, guys, what unit is that? That's 1.67 what? Meter per second. Yeah, it's talking about velocity. Right. The kilograms cancels out. Okay, there. So fast. Good thing you do when you get an answer is say, does that look like it makes sense? Okay, well, I have a little mass going pretty fast, slamming into something that's like 5 times its mass, going a lot slower. Yeah, those terms are about right. Right. I'm gonna do a kinetic energy check. Kinetic energy check. Right. because I've been saying kinetic energy needs to decrease for this type of collision. Okay? So what is kinetic energy initial? What is kinetic energy final? Like pre-collision and post-collision. I'll just do this on my calculator screen, but you guys know 1/2 mv squared, right? So let's do 1/2 times this mass times this speed squared plus the other one was also in motion, 1/2 times its mass times its speed squared. Okay. And I'm getting 15 joules, right? 15 joules pre-collision. Right. How about post-collision? Let's do 1/2 times the sum of the masses, which was this many kilograms, times their collective speed, 1.67 meters per second, and square that. Right, so that's like 8.3 joules. Yeah, the kinetic energy definitely decreased. Maybe they just wanted to deform each other. Maybe they warm up a little bit. Right, so the energy didn't disappear from the universe, but it did decrease mechanically. Oh, yeah, answer choice right there. Boom. All right. All right, you guys get there? All right, let's check out number 6. Ooh, a grenade flying through the air. I think I mentioned yesterday that you get questions like this. Oh, AP loves these kind of questions too. So for sure, you're going to get 1 or 2 of these, right, on the AP exam. Very similar to what we're about to do right here. Grenade flying through the air at some given velocity explodes into 2 parts. Pow! That travel along the same direction the grenade was originally traveling. Okay, so like maybe along the x-axis, something like that. At what velocity is piece B of the grenade traveling? Hint, applied perfectly inelastic just in reverse, right? Because if you film this explosion and you put the film in reverse, it would look just like an inelastic collision, wouldn't it? Right? In fact, if you followed kinetic energy, I bet the kinetic energy, and this one says it's also backwards of inelastic collision, I bet the kinetic energy is going to increase because it comes from somewhere, it comes from the explosion, right? That chemical reaction, bow, is going to add kinetic energy to the system. Okay, so number 6. Let me do a wider picture. Right, so you throw this grenade, say it goes into like a parabola type path, and let's have it explode like right at the top of the path. Right? So right here, pow, it's gonna explode. Okay. It was traveling at some initial velocity, V naught, right? But then there's 2 separate parts. They're gonna do their own separate things. Right? And I can solve this with conservation of momentum because it's just a reverse collision, right? An explosion is just a reverse collision. Think of it that way. Okay? So sum of momentum before the collision, or before the explosion, rather, right, is equal to sum of momentum after the explosion. Okay? And before the explosion, it was just one giant grenade. So I'll put mass A plus mass B, right? Because it was all just one thing, moving at some initial velocity. And then after the explosion, you have 2 separate pieces, each doing their own thing. MAVA final plus MBVB final. Okay. Okay. All right. And the question is, what is this right here? Right. So we should be able to just plug everything in. Let's go do that. All right. So I got 0.3 kilogram plus 0.7 kilogram. Okay, so I had a 1 kilogram grenade. It was moving at, my paper says this many meters per second. So pop it in. Right. Then piece A, which was this many kilograms. Right. Let's say we determined. Oh, whoops. Nope, I got some numbers messed up. Oops, I'm misreading my own table. Okay, let me change this one. That was that fast. Oops. This was all right. This fast post collision. Right, and then mass B, this many kilograms. Right. I'm just trying to get a multiple choice answer on my own paper, so make sure my numbers are matching up. Okay. Okay. And then this we're solving for. Okay. So we know everything except one thing, then we can solve for it. Just like that, right? Okay. Right. So we do some math here. So I got this many kilogram meter per second momentum in the system before. And then some of it goes into this guy. Right? And then whatever's left goes into piece B. Right? So I can finish with algebra. So I'm going to do that minus that. And then I'm going to divide by that coefficient mass right there. Right? So that minus that, and then divide by that. You guys have done like so much algebra in this class, right? Like that. So piece B has a final velocity of this many about meters per second. There you go. Okay. Right, so does that make sense? Right. Well, looking at my numbers, see, I threw this grenade and at the top it was going like 35 meters a second. It explodes in two parts. One of them slows down to almost 0 meters per second. Right. I mean, well, sorry, like I guess a third of its original speed, right? But that's a tiny mass, so it gains has very little of the momentum, right? So the other one has most of the momentum, right? And it has the speed up, right? All right. So how could we kind of like figure this out? We can figure this out by seeing where the grenade pieces land. So that's something I haven't drawn here. Let me switch to pink ink. Right. So like before the explosion, or what if the grenade never exploded? Well, it just very simply would have followed this whole parabola path. Right? But what actually happens is it explodes right there, and then the two pieces each go on their own journey. One goes falls down there, and it goes like way ahead, something like that. Right. So one lands pow right there, the other lands pow like way ahead in the field. Right? Maybe what actually happened is we're trying to find the grenade piece. We said, well, there's probably a couple grenade pieces, and oh, hey, here's a big chunk of it right here. We found this on the ground. Oh, I wonder where is the other piece? And say, well, I know pretty well how fast I threw it. And I see we've got about a third of the mass here, so the other 2/3 of the mass, but okay, blah, 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 right? And basically, do an extended version of this question, and you can have a pretty good idea of where the other piece lands, right? You guys get the idea? Right. Okay. How about this? What if you followed just the center of mass of these two pieces, the center mass of the two pieces, right? Guess where the center mass has to land? Exactly as if it had never exploded at all. And AP always asks that question. The question I just asked, here, I'll say it again, because you are going to be asked that question on an AP exam. Okay? If you just follow the center mass lands between these two pieces as if it had never exploded at all. So if it never explodes, or if it goes through a small explosion, or if it goes through a large explosion, right, scatters these pieces like to the wind, right? If you found like the center mass of all the pieces and put them all back together, the center mass would be exactly as if it had never exploded at all. Okay. Right? Sometimes they word that question slightly differently, but some version of that question you're definitely going to see because they always like that. Yeah, ask that question. Okay. You guys get there with the grenade? Okay. All right. Number. Oh, let me make sure I got an answer. That's that answer right there. Bam, got it. All right, number 7. Two objects given masses collide head on perfectly elastically. Therefore, what's the final velocity of object A? Right. So this is one. If you get this one in college, then they would expect you to solve a system of equations from scratch, and it would take a lot of paper and a lot of time. What I'm going to do instead is find my poster version of it. Here it is, where I've got this thing pre-solved. Right. So here's my pre-solved version. Right. So just for this paper, we're just going to jump straight to this yellow box, which is the solution to the system of equations. Remember, perfectly elastic means not only is momentum conserved, which is true for any kind of collision, but also kinetic energy is conserved, which is special to this type of really bouncy collision. Right. Now, how would you answer this on an AP question? Right. Because I've seen AP ask this question, but I think the best way to answer on an AP is to play off their multiple choice answers. So you go through A, B, C, and D, and you test individually and say like, I think that your upcoming AP classroom, I think this question might show up there. Right. So is momentum conserved? But also, especially if they use the word elastic, I would break out kinetic energy and start running 1/2 mv squared to say, is the kinetic energy also conserved? So the sum of 1/2 mv squared before and after the collision. Because if it is, then that would be the correct multiple choice answer. And there's only one solution that could ever possibly lead to kinetic energy being conserved. Right? If it isn't, then it would not represent an elastic collision. Right? Okay, go ahead.
If you were to plug in an axis like that, would you also need to solve the velocity of
No, I've never seen AP expect you to solve this or memorize this. I mean, if you do memorize this, I mean, it could always help you out. But there's only so much headspace everybody has and so many things to memorize. So maybe I wouldn't recommend it just so you could allocate your time towards like studying other things, right? Yeah, I've never seen AP expect you to solve the system from scratch and actually solve for the post-collision velocity. Okay, but let's go ahead and do that anyway, just for this one. So I'm going to say velocity A post-collision is velocity A pre-collision times the difference of the masses, plus 2 times the other mass times its initial velocity, because we're looking for velocity A post-collision. And here I got mass B and velocity B pre-collision, right? So just the opposite mass. And then all divided by the sum of the masses. So pop in numbers right here. Right, so just pull these numbers straight off this table. So we got velocity A initial was this many meters per second. Difference in masses, this many kilogram minus this many kilogram, plus 2 mass B, VB initial. Looks like mine was starting at rest, so that's interesting. Okay, yours may or may not. Okay, start at rest, okay, for one of the masses. All divided by sum of masses. Got this many kilogram plus this many kilogram. Like that. Okay. Going there. Whatever. Okay, let's run the numbers. Run the numbers. Okay, so 5 times that minus that. Okay, that all zeros out. All divided by 4.5. Okay, so I'm looking at this many. Okay, so I'm getting a number on my screen. Guess what's the units attached to this number? This is how many what? Meters per second. Yeah, because we just solved for a post-collision velocity, right? So it's positive. That tells me something about the direction it's going. We make sure it's an answer choice. Yeah, answer choice right there. Bang, got it. So good on that front. Right. All right, here's the thing. Okay. So again, that's for an elastic collision. The closest thing I have in front of me to elastic is probably this. Also, your collision carts. If you just have one with the inbuilt magnets, it's going to model pretty close to elastic. So it's something about like that. Oh, you know what? If you're keeping track of what do we know and what do we not know? Okay. So I know both masses; those were given. I know the pre-collision velocities; those were given. Okay. I know the post-collision velocity of object A. This is V sub A post-collision. Right. But you know what we don't quite have yet is the post-collision velocity of object B. Ooh, right. I could think of different ways to get the post-collision velocity of object B, which I neither gave you nor do we have solved here yet. Right? How could you get the post-collision velocity of the other object? What's one way to do it? Hey, could you just change the definition of what's object A and what's object B? Could you put V sub B final is, and then change that to B, and then B minus A, and then A, and then B plus A? Could you just do that? Hey, you could just redefine the objects, right? And that would do it, right? Because you would have all that information. But all this is given values to still be given values pretty quickly. Another thing you could do is now that you know what the post-collision velocity of one of the objects is, because we just got that, you could go back to either one of these green equations right here. And you say, well, I know everything except for VB final, or in this case, VB final, right? And either one will tell you the same answer, right? Because that's the way you do it. Right? Again, if you see this is a multiple choice question on an AP exam, probably the fastest way to do it is just to go through the answer choices A, B, C, D until you get something that actually would be consistent with either one or both of these. Right? All right. Number 8, 2 objects collide head-on, and resulting in these velocities. I gave you before and after velocities. Notice I did not give you the masses of the objects, right? Which you don't actually need to answer this question. What's the coefficient of restitution between 2 objects? It's like how bouncy is it, right? I'll have you guys do a lab probably next week, and I'm also like bouncing balls off the floor. If we give you like a tennis ball and a bouncy ball and a little racquetball, right? Those all bounce differently off the tile floor, right? So that's like the ball versus the earth, right, on a tile surface, right? So maybe something like that, where it didn't give you the masses. Okay, so this is one of these concepts that will not appear on the AP exam, but good to know about anyway, right? Coefficient of restitution. So I can do, what is the post-collision velocity? B final minus VA final. So that post-collision difference, zoom out where you guys see this, right? There's the post-collision difference in velocities compared to the pre-collision difference in velocities. So VB initial minus VA initial. Right. Now, whenever you have a collision that bubbling has some kind of rebound, there will be some kind of reversal in direction for something. Right? Something has to reverse direction, possibly both, possibly one. Okay? Which means that as I wrote this, this will always come out to be a negative number. And there's a few ways you can handle it to always make it a positive number, just so it looks a little prettier. Right. One way is you can take absolute value. Another thing is you could swap A and B, saying either the numerator or the denominator. Third option is I can just slap a negative sign on the outside, right? And those will do it. So let's get coefficient of restitution for this bounce. Right, so VB final, I just plug in these numbers. I got 3 meters per second minus VA final is -1 meter per second. Remember, when you're subtracting a negative, that's kind of like adding a positive. Okay. And then compared to before the collision, I've got that many meter per second minus that many meter per second before the collision. Okay. Right, so it's in the calculator. So 3 plus 1 is like 4, all divided by, that's -12, but make that negative, so that could just be 12. Okay. I'm getting this number on my calculator screen, which is also an answer choice, so I'm good on that front. Okay. Guys, remember, a coefficient restitution is always going to be bounded between 0 and 1. 0 is perfectly sticky, 1.0 is perfectly bouncy. Right? So, look at that. All right, so this is going to be a pause point today. Yeah, we just got a few more on this page, and then tomorrow is going to be back in the lab area for Inelastic collision lab. All right, there's a pause point today.